For x approaches a, f of x, when we evaluate f of a, we get the following situations. Non-zero over non-zero, which equals a non-zero. A 0 over non-zero, which equals a 0. A non-zero over 0, which is an asymptote. When we have the 0 over 0 situation, we have to use intuitive limit laws to manipulate our function into an equivalent form that doesn't have that division issue. F of x equals f of g, where x doesn't equal a, then limit as x approaches a of f of x equals limit as x approaches a of g of x. Since limits don't consider what actually happens at a, we bypass our original division issues. We can compute limit x approaches 1, x squared minus 1 over x minus 1, limit x approaches 0, square root x plus 1 minus square root 1 over x, and limit x approaches 0, 2 sine x over sine 2x, using factoring, conjugates, and trigonometric identities, respectively. We have the following. Often, we consider factoring expanding, usually with polynomials, and conjugates, usually with radicals. Calculate limit x approaches infinity, square root x squared plus 1 minus x using conjugates. We cannot substitute infinity. We have the following. What is a number x that is or at least 5 and that is or at most 5? The number x is squeezed between 5's, and so x equals 5. The idea of squeeze theorem is if f of x less than or equal to g of x less than or equal to h of x, and limit as x approaches a of f of x equals L equals limit as x approaches a of h of x, then limit as x approaches a of g of x equals L. Compute limit x approaches 0 x squared sine 1 over x by first noting negative x squared less than or equal to x squared sine 1 over x less than or equal to x squared, and using squeeze theorem. Here is a picture. Start with sine x, which is between its range. A different input does not affect range. Multiply by x squared. Take the limit as x approaches 0 on its ends. Evaluate limits on the ends. Applies the squeeze theorem. Compute limit theta goes to 0, sine theta over theta, by using some geometry and squeeze theorem. Here's a picture. Start with small theta. Arc AB equals theta. Length BC equals sine theta. Length AD equals tan theta. Divide by sine theta. Reciprocate each term and flip inequalities. Take limit as theta approaches 0 positive on the ends. Evaluate limits. Sine theta over theta is an even function, and squeeze theorem. Compute limit theta goes to 0 cosine theta minus 1 over theta by using conjugates, trigonometric identities, and using our previously solved limits. We have the following. We can compute limit x goes to 0 sine 3x over 4x, limit x goes to 0 x cotan x, and limit theta goes to 0 cosine theta minus 1 over sine theta. We have the following. Note, for the first limit, if theta equals 3x, then as x goes to 0, theta goes to 0. Continuity. A function f is continuous at a point a if limit as x approaches a of f of x equals f of a. Visually, this means the graph of f has no holes or breaks. There's also continuity from the left and right that used one-side limits. We can show that f of x equals absolute value x is continuous at x equals 0 since limit as x approaches 0 of absolute value x equals 0 equals absolute value 0. A function being continuous is different from being continuous on an interval. Continuous functions are continuous at every point in their domain. Continuity on an interval means continuous at every point in the interval. So, for example, 1 over x is a continuous function since it's continuous on its domain, x not equal to 0, but it is not continuous on intervals with x equals 0. If f is continuous at b and limit x approaches a g of x equals b, then limit x approaches a f of g of x equals f of b. And we have the following. This means that we can find limits inside of continuous functions. We can calculate limit as x approaches 1, like sign of this. We have the following. Discontinuity. If f is not continuous at a point a, then it is discontinuous at a. Limit as x approaches a, f of x does not equal f of a. All these functions are discontinuous on intervals with x equals 0. Respectively, these discontinuities are removable, a point, jump, a step, oscillating, and infinite. Intermediate value theorem. A tree grows from 1 meter to 2 meters in a year. Sometime in that year, the tree was 1.5 meters. Intermediate value theorem. A function that is continuous on the closed interval ab has a c in open interval ab such that f of c is between f of a and f of b. Visually, the graph of a continuous function takes every x and y coordinate between the x and y coordinates of its endpoints. For example, we can prove that f of x equals x has a root. Note that x is continuous, because it's a polynomial, on interval -1 to 1, and f of -1 equals -1, and f of 1 equals 1. And so, by the intermediate value theorem, f of x equals 0 somewhere on -1 to 1.